Welcome to this tutorial on behavioral modeling of logical circuits on Xilinx software. So, in this tutorial, we will implement one or two multiplexers using behavioral modeling, and then we will simulate them, right? So, this is a multiplexer module, 2 to 1, 2 input, 1 output multiplexer module, and this is the circuit inside it, right? So as we know, in behavioral modeling, we are not concerned with this circuit inside the module. We only describe the behavior of this module. So if you look at it, so the behavior of this module is when this selection line S is 0, the input I0 will be selected on the output, and when this selection line S is 1, input I1 will be selected at the output. So let's write a Verilog code for this multiplexer. So before that, uh, so let's begin by creating a new project. So so go to the files option in on the Xilinx, and then click on the new project. And here you need to write the name. So let this name be behavioral modeling mux, right? So and then you need to select appropriate directory for this module, so which I have already selected. Now click on the next and next and, and finish. So now you have already created this project. So now in this area, so this area is the project planning area. So here you right click and then click on the new source, and from here you select Verilog module, and then you write the name of your module. So let's call it, the first multiplexer is 2 to 1, so let's call it mux 2 to 1. So and then click next, next, and then finish, right? So let's go back. So we have two inputs, in 1 and in 0, a selection line and an output, right? So let's uh, let's write input and output. Let's say our output of the multiplexer is out, and the inputs are in 1, in 0, and in 1, and the selection line, let it be select, and you can remove that, right? So now out of these inputs and outputs, you specify which one of these are input and which one of these are output. So let's first specify output. So so out is our output, and so use input keyword to specify inputs. Right, so these are our inputs, and then so in behavioral modeling we generally use this always block that allows us to repeatedly execute uh, the, the behavior that we have specified for a certain logical circuit. So let's write this always command, and then you use this add. So here you specify the the conditions so which essentially become the reason to execute this always block. So so generally we specify all the inputs, so in 0 or in 1 or select, right? So this means, so whenever there is any change in input 0, input 1, or select, this always block will run, right? So now let's write the if statement. that to describe the behavior. So if you look at it, so we need an if statement that specify if s is equal to, or select in our case is equal to 0, I 0 should be selected, and when this select is equal to 1, I 1 should be selected, right? So uh, so let's start with the if statement. So write begin, and then if, and so here you write select the condition. If select is equal to, so this double equal to sign is basically the equal sign in Verilog, and here you specify 0. So so right. So generally we do not specify a binary digit in this way. We specify a binary digit by first specifying the number of bits. So the number of bit in this binary digit is R1. So and then we write this single quote, and then we specify type, its type. So we are writing a binary digit. So and then we write the actual binary digit, right? So this is how we write a binary digit, right? So if you say if we are writing two binary digits, so we will first specify the number of bits in this binary digit. So if we are writing a 2-bit binary digit, sorry, 2-bit binary number, then we will first specify the number of bits, and then we will specify the type, and then we will specify uh, the number, right? So this way you can write binary numbers in Verilog. So since we are only uh, writing 1-bit binary number, that is 0, so we will write 1 here, and then the single quote, and the type, which is binary, and then the number, the binary digit itself, right? So this is the binary digit that we want to write, but before so in order to write this, we need to specify the number of bits and its type, right? So this way we can also write the uh, hexadecimal numbers, the octal numbers, and decimal numbers. So we need to specify the number of digits, the type, and then the digit itself, right? So but we are only in this particular tutorial, we will restrict ourselves to this binary digits. So now so once we have this condition, so now but we will specify what should happen if this condition is satisfied. So if this condition is satisfied, this out should be equal to uh, in 1, right? So sorry, in 0. So if this in selection line is 0, select is 0, the out should be equal to in 0. And then else, so, and, so and if say this condition is not satisfied, it means this binary digit, the select is not equal to 0, which means select is 1, and in that case out should be equal to, or instead of this, in fact this is not an equal sign, this is an assignment statement. So it means this out, the output should be equal to the input 1, or input 1 should be assigned to output, right? So now we specify the end. So this end is the end of this begin statement for this if statement. So uh, so that's it. So we have successfully written this code for 2-to-1 multiplexer using behavioral modeling, where we have specified the behavior using this if else command that starts with a begin and ends with this end, right? So let's save it, and then click on the simulation, and then click on this uh, the name of the module, and then you will see this ISIM simulator. So here you click on this plus sign and click on this behavioral check. So apparently we have run into errors. So what could be the issue? So let's see. So The error here is because we have not defined this output as a register, because we want to change the value of this memory element out during the execution of the program, and in order to do that we need to define this as a register. So we will specify that this out is of register type. So once you do that, you will not get this error, right? So I intentionally left this out for you to understand how important this definition of this out as reg type, right? So now once we have done this, let's save it, and you can again click on the name of the module and then click on this behavioral check, and you see this is now it is perfectly fine. So there are no errors. So now we can move to write uh, its test bench. So let's click on the new source on this. So right click on this on this project plan window. So click on the new source, and then at this time select test Verilog test fixture, right? So like so then, and then name it as tb underscore in the name of your module. So mux, and right. So this is the name of your test bench. Make sure that the location or directory is the same as the directory of your project, and now click next, and then link this module, this mux221 module, with this test bench. So select this mux221, which is already selected, click next, click finish. So you will get this window where you can write your test bench. So you already, it has defined the inputs and outputs in a certain way. So we again define inputs as reg type because we want to change its values during the execution of this program. So we write this test bench. So let's let's specify the truth table. So let it be 0 0 when selected 0, and then 0 1, and then so 1 0 and 1 1. So for all these input changes, I've kept the select input as 0, and now you copy this all code and then paste it right under here. So now you just change the select for the next part of this code. Just change the select input to 1, right? So this is the truth table for containing all possible input combinations, right? So now once we have specified this the inputs and outputs in this test bench, so let's save it, and now click on simulation, which we have already clicked, and so here click on this name of the test bench and run its behavioral check. So you see there are no errors, and now we are ready to simulate it. So once we have simulated it, so we have ended up here. So as you can see, so by clicking on this fit to screen or zoom in window, you will end up to the area of the plot that concerns us. So as you can see, when select is 0, so until here select is 0, and in this case the output is in 0. So whatever is at the input 0, as you can see, whatever is at the input 0 is on the output, as you can see clearly, right? So this is input 0, so this is input 0, and so as it is changing from 0 to 1, the output is also changing from 0 to 1 for the same in the same way, right? But when this select line changes to 1, as you can see, this now suddenly the output is now same as the input one. So this is output and this is input one, right? So this is input one, and so this is, so the output is very so when select is 0, output is input 0, and when select is 1, output is input 1, right? So now so uh, let's go back and then add this finish command here. So instead of clicking on that zoom button, you could use this finish command that would end your simulation. So at the end of the last delay or the time that you have specified. So now save this and run its behavioral check, and now simulate it. So you see there are some errors. Yeah, so this error generally arises. So this error is unable to remove previous simulation file ISIM. So it means you need to close the previous file, and then you will see this error failed to link to design. So you go to this LSIM simulation that you previously uh, run, and now you close it. So now you run it or run this behavioral model again, and this time you will, so this time you need to rerun all. So it will end up here, but it doesn't mean that the simulation has not run. So this means this particular message is telling you that the simulation is ended after, say, 800 seconds, right? So 800 nanoseconds, right? So but else, so instead of, so you need to uh, click on this window where you can see your simulation, and then by clicking out on the same, you'll see it exactly ends at 800 nanoseconds. So you don't see the part where which is not concerned to you, right? So uh, that's it. So this is how we simulate our 2 to 1 2 to 1 bit multiplexer. Now let's write behavioral modeling code for a 4 to 1 multiplexer. Let's right click on this window, click on the new source, select Verilog module, write the name, let's call it mux 4 to 1. So let's click next. So I've since I've already created a file with the same name, so it's asking me whether you want to replace it or not. So yes, replace it. I click next and then click finish. So now it's also asking me to close this window. So let's close this simulation window, right? So now you can start writing the code for a 4 to 1 line multiplexer. So let's first specify the outputs and inputs. Out in 0, in 1, in 2, in 3, in 4, and select, right? So and then you specify which one of these are inputs and which one of these are outputs. So output is out, and you would want it of type reg. So specify uh, the type here, and then specify the inputs using this input keyword. So and then you specify select. So since this select input is so in this case I want to define it as a vector of 2 bits, so I'm using another keyword. So to define it as a vector is, this is how we do it. So you specify the places of the binary digits. So the first binary digit, so the two binary digit means there is a binary digit at for place for the units place, and so 2 raised to power 0, and then there is a digit that is for ones place, or sorry, two's place, that is 2 raised to power 1, right? And then you write the name of your array or the variable, and once you have specified the inputs and outputs, it's time to write the always command, and then you write this at. So after that you specify the condition that allows it, or that enforces this block to run. So in this case, as we have already discussed, we generally use all the inputs for this purpose. So let's say in 0 or in 1. So OR is basically this OR gate. So we so any of these inputs is changing, then uh, this this condition will be true, and always block will be executed, right? And finally, the select input, this which is the input that we are using a selection line. So use of this select is absolutely necessary in this always block for as a condition to execute this block. So once you have done this, now use the case statement. So use case keyword, and then write this input to this case keyword, which is select, which are our selection lines. So when selection line gives you 0 0, it means you need to select the input 0. So so this select is, we know this is a vector, so it has 2 bits. Specify the number of bits or the digits, this uh, this quote, and then the type. So we are using this binary digits. So and then you write the binary digits or digits, right? So this is the case 1. So in this case you want your output or out to be in 0, right? So this is how, or this is what uh, this is uh, a, this is a 4 to 1 multiplexer. So when the selection lines are 0 0, you would want this I0 to be selected at the output, right? So when selection line is 0 1, you want I1 to be selected, and this when this selection line is 1 0, this you want I to be selected at the output, and when this selection line is 1 1, you want I3 to be selected at the output. So you can so this is what we are doing in the case statement. We are actually implementing these cases, right? So uh, so when we get this situation, uh, in this case we want output to be equal to input 1. So in this case we want output, so in case of 1 0, we want output to be equal to input 2. And for the case of 1 1, we want out to be equal to, or we want to assign input 3 or in 3 to the output or out in this particular case, right? So now end this case statement, and I guess that's it. Now you need to run this. We have successfully wrote this behavioral code for this 4 to 1 line multiplexer. Now let's save this, and select it and then run its behavioral check, and it says input 1 is not declared. So input 1 is actually, it is absolutely right. So we made a mistake. Yes, input 1 is missing here. So it's very clear. It is saying that input 1 is not declared. We are using input 1 here and here, but we have not actually declared it. We did not. We missed it. So let's save it again and run its behavioral. So hopefully this will be all right. Yeah, it's fine now. So there are no errors. Now we can write a test bench. So again, right click on this window, select the test fixture, write its name, let it be tb underscore mux 4 to 1, and then click next. So now select 4 to 1 because in this case we want to write the test bench or test fixture for this mux 4 to 1 line multiplexer, right? So in this case, so once we click on the finish, we get this window where inputs and outputs are already declared, and here we need to write the input combination. So let's say we, I guess we did make another mistake. We have defined an extra input that we are not supposed to define. So let's go back on the and remove this because we are not supposed to define. We need to define 4 inputs and which comprise of in0, in1, in2, and in3, right? So save it again, run its behavioral check, and we are not supposed to use info, right? So we save it. So we have run into fair bit of errors, but finally we have overcome them. So it's a good experience to be able to remove these errors or troubleshoot. So I hope you might have learned something extra today in this tutorial. Okay, so now once you have done this, now let's again start with the test bench. Now again you go to the window, right click, and then select this Verilog text fixture, name it mux tb underscore mux 4 to 1, and then click next. So since we already made the attachment with the same name, so we need to replace it with that and select 4 to 1 multiplexer, click next, finish. So now you have you end up with this window where you can write your test bench. Inputs and outputs are already defined, so you need to specify the different type of input combinations. So first of all, let's in this particular test bench, let's keep the inputs same and only change the selection line, right? So since the select is a binary number with two bits or 2 digits, so let's write it in the appropriate format. So this is how we should write it. So this is the first instance where we want to select in 0, and then now you change it to 1 0, right? So you keep the inputs same and you only change the test bench, sorry, the selection line. So this should be, in fact, this should be 0 1, and let's make it 1 0, and let's make it 1 1, right? So this is a different type of test bench that we have made. So it's up to you what kind of test bench you want to make. Instead of listing all possible input combinations here, we have only we have kept the inputs in 0 to n3 very same across all input combinations, and we have only changed the selection line, and now we will be able to see whether the relevant input is selected or not for a given input select line, right? So that's it. So this is now let's save this test bench and click on this test bench and then click on this run its behavioral check. So it's fine. Now let's simulate it. Uh, so here we are. Click on this zoom to fit button. As you can see, for input 0 0, the input 1 is 1, so it is selected. For input selection line 0 1, you can see the output is basically this input 1, which is 0, and so the output is also 0. And in case of input selection line 1 0, you see the output is 1, and it is because this input 2 that is supposed to be selected here is 1, right? So it is selected for this period, and when this input is 1 1, you see the output is selected as input 3, which is 0, right? So for a more detailed truth test bench, you could list the truth table for 5 inputs, maybe 6 inputs, and then you would be able to see a more detailed uh, output response, right? So that's it.